Hello. Let's do a problem that kind of seems similar to the ones we've been doing in the last few videos, where both players' payoffs are A times B, but now we'll constrain A and B, where A and B must both be greater than equal to -1 and less than or equal to 7. Why don't you pause the video and try to make some progress on this problem? Okay, let me give you a hint. This game has multiple Nash equilibria, so if you only found one Nash equilibria, why don't you pause the video again and search for another? Right. Now, player 1 maximizes A times B, treating B as a constant. Well, we take the derivative of A times B. If A is the variable and B is the constant, we get B equals 0. But don't go setting B equal to 0, because remember, player 1 controls A. Player 1's first order conditions are telling him to set B equal to 0. We've got a bit of a problem because player 1 has no control over B. The calculus doesn't work here. So what's going on? Well, you've got to actually think about this problem. We can't use normal calculation maximization techniques. Remember, players' payoffs are A times B. Now, for player 1, if B is positive, player 1's payoff is increasing in B, and he'll only not regret setting A at its highest possible value. So if B equals 3, player 1 wants to make A as big as possible because that maximizes his payoff. And in this game, that would be 7. Now, if B is negative, two negative numbers, you multiply them together, you get a positive number. So if B is negative, player 1 wants to set A at its lowest possible value. So if B is, say, -0.5, player 1 wants to set A at its lowest possible value, which is -1. Finally, if B is neither positive nor negative, it's in between, it's 0, well then player 1's payoff is 0 no matter what, and player 1 becomes completely indifferent to setting his payoff equal to anything. Setting A equal to anything. So when we put this together, since I've made the payoffs for both parties symmetric, they're both equal to A times B. The Nash equilibria are where they both set their choice variable equal to 7, they both set it equal to -1, or they both set it equal to 0. Let me give you sort of a verbal proof of why. Right? If A is going to be positive, then the only time player 2 won't regret his decision is setting B at the highest possible number. And if B is set only at the highest possible number, the only time player 1 wouldn't regret is if A is at its highest possible number. So there's only going to be one Nash equilibrium where either A or B is greater than 0. And that's where both A and B are at their greatest possible values. Similarly, if A or B less than 0, there's only going to be one Nash equilibrium where both A and B are its lowest possible values. Because if A is below 0, player 2 will regret not setting B at the biggest and absolute value negative number it can, which is -1. And if B is below 0, player 1 will only not regret setting A equal to -1. So there can only be one Nash equilibrium where either A or B is below 0. Finally, we have to look at the 0 case, and there is a Nash equilibrium if both A and B are 0. Because if A is 0, player 2 is indifferent among doing anything, so he's willing to set B equal to 0. And if B equals 0, player 1 is indifferent among doing anything, so he's willing to set A equals 0. Now, there can't be a Nash equilibrium where A is 0 and B is non-zero. Because if A were, let's say A is 0 and B is 3. Well, player 2 wouldn't regret his choice because he's getting nothing no matter what he does. But player 1 would regret setting A equal to 0. If B equals 3, player 1 set A equal to 0, and player 1 realized B was 3, he would say, oh gee, I regret this because had I known B would equal to be 3, I would have wanted to set A equal to 7. So these are the only 3 Nash equilibria. Now this Nash equilibria, these two might seem strange because both parties are getting 49 in this one and they're getting 1 here and they're getting nothing here. But in a Nash equilibria, that doesn't mean you're getting your highest possible payoff no matter what everyone's doing. It just means you're getting your highest possible payoff no matter what you're doing. And if, B equals -1, the best player 1 can do is set A equal to -1. So again, always imagine when you're trying to figure out what the Nash equilibrium is, you're actually playing these kind of games. So both people are playing the game. They both simultaneously write down their choice. Player 1 writes down -1, player 2 writes down -1. They reveal. Player 1 won't regret having written down -1 if he sees that player 2 wrote down -1, because given what player 2 does, player 1 can't do any better than respond to -1 at B with -1 at A. Remember, in the Nash equilibrium, while you have control over what you're doing, you don't think you have any control over what the other person is doing. So you treat their choice as exogenous, as fixed, as beyond your ability to influence. So you don't, if you end up here, no one regrets because no one thinks they can move from here to here. All you can do is control your individual choice. So if A is equal to -1, player 2 is not going to say, oh, gee, I wish I picked 7, because that would give him a horrible payoff. Player 2 would only regret not pitting B equal to -1. Thank you for listening.